Okay, so let us take a quick introduction to Hamiltonian. Although it's a part of your master's course, but I felt here some necessity for you to get acquainted with this object. Okay, so we have done in great detail what do you mean by Lagrangian and Lagrangian equation of motion. So consider you have a ball moving along the positive x-axis with a momentum p and mass of the ball is m, and say it is moving with a velocity v. Although the momentum p contains the information of mass and velocity in itself. Actually, it contains the product of mass and velocity, to be more precise. So it is moving along which direction? Along the x direction. So velocity can be given by x dot, because we know that velocity is nothing but dx by dt. So we have done all this stuff before. So if I ask you the Lagrangian, then we know that Lagrangian is a function of x, it's a function of x dot, and it's a function of time. Okay, this is our actual Lagrangian for 1D systems. In this case, the Lagrangian is independent of time. So let me write it's a function of x and x dot. But this is also not true, because the Lagrangian is only dependent on x dot. Let us see why it is dependent on x dot. Since it is a free particle, so it has only kinetic energy, which is half m into velocity square. Velocity is x dot. Do you see any dependence on x? There is no dependence on x. Okay, because there is no potential. This is example number 1. However, I can give another example where your Lagrangian will be a function of x and x dot both. Let us see. Consider a spring mass system. We have discussed in great detail about the spring mass system. So what is the Lagrangian for a spring mass system? Let us see. And let me tell you in advance that this Lagrangian will be a function of x and x dot. Okay. So the mass will have kinetic energy, so which is given by half m x dot square. But at any time t, the mass is also going to be under some spring potential. So it is half k x square. There is a minus sign because Lagrangian is kinetic energy minus potential energy. You know, this is the kinetic energy T, this is minus, this is V. Okay, here the Lagrangian is a function of both x and x dot. Quite clear. Now you know how to use, there is something called as Lagrangian equation of motion. So once you define a quantity called as Lagrangian, then it has a Lagrangian equation of motion related to it. And we have already studied, it is d by dt of del L by del, so I am writing for one dimension, okay, x dot minus del L by del x equals to 0. So what Hamiltonian thought is, Hamiltonian says that okay, everything is good. If you define a particular Lagrangian for a particular system, all you have to do is solve this Lagrangian equation of motion and you get everything about the system. But he was not happy with this thing. He said that if you look at the first term carefully, there is a second order differentiation. He said that sometimes when you get second order equations or second order differential equations, then you face trouble. So he said, let us do something so that instead of second order, we get first order equation of motions, which will be easy. So then Hamiltonian said that okay, instead of defining the Lagrangian, let us define something called as Hamiltonian of a system. See, Lagrangian of a system is what? How to define? If a system, if you know the kinetic energy of a system and you know the potential energy, you subtract them, you get Lagrangian. And you also found that Lagrangian is a function which is a function of position, x dot and t. See, I'm still talking in the regime of 1D. Okay, I'm still talking in the regime of 1D. Hamiltonian said, I am going to define a new function, Hamiltonian, which will be a function of x. Instead of x dot, it will be a function of p and t. This brings a huge difference. Don't you think Lagrangian is equal to Hamiltonian because P contains the information of x dot anyhow? No, no, no. P has both m and x dot. It's a function of momentum and x dot. So don't you think Lagrangian is equal to Hamiltonian? No. So he said that we can define this for a system, and for this he will say that I am going to find equation of motion which will be not in second order but in first order. So he said instead of defining the Lagrangian of a system and getting a second order differential equation, you define the Hamiltonian of a system and get the first order differential equation, and life will become easy. Everything will be easy to solve because first order equations are very easy. We know this from our experience in mathematical physics. Okay, now how to find Hamiltonian. So he said that we can find the H from the Lagrangian. If you know the Lagrangian, just do this much. Take the P. What is P? P is the canonical momentum. Let me remind you, P is del L by del x dot. This is the canonical momentum. So he said that take P, multiply with x dot, and subtract it with the Lagrangian. If you do this, you get the Hamiltonian. And this Hamiltonian, let me write it in more precise way. Yeah, and this Hamiltonian will be a function of what? As I said, this Hamiltonian will be a function of x, p, and t. Okay, so this is how you find Hamiltonian from the Lagrangian. Define the Lagrangian and then do px dot minus L. Remember, this is for 1D. Okay, now what is this P? This P is this, which is the canonical momentum. Okay, everything is clear till here? Okay, how about 2D? Let me define 2D. So in 2D you have both axes, x and y. So your Lagrangian will be function of x and x dot, and it will be a function of second axis variable y and y dot and time. This is your 2D Lagrangian. Then how to find Hamiltonian in 2D? Now in 2D the Hamiltonian will be a function of x and momentum along x direction. It's a function of y and momentum along y direction and time. This is equal to, so now you do this. Find the px and dot and multiply with x dot. Then find py and multiply with y dot, and then subtract it with the Lagrangian. Which Lagrangian? This Lagrangian. So this is Hamiltonian in 2D. So let me write the general expression for Hamiltonian. Okay, let me write it here. So the general expression for Hamiltonian is, so if there are many dimensions, say there are n dimensions, then the Hamiltonian will be given as, so let's write it here. The Hamiltonian will be given as, it's a function of q, so we write qi, I goes from 1 to n. It's a function of pi, I goes from 1 to n, and t. So the general expression is equal to, then there will be summation of I. So if I is 1 to 2, like in 2D, you get only 2 terms. If I is 1 to n, then you will get many terms. So we write pi, and we use the generalized coordinate qi, but there will be qi dot minus the Lagrangian. And remember, Lagrangian will be a function of qi, because I goes from 1 to n, qi dot and t. All clear? Okay. So now that we have defined the Hamiltonian, now the question is how to understand Hamiltonian in more proper way. Okay. So the best thing we can do is look at an example.